Okay, so as you're still continuing, we'll start with the launch vehicle. So what is the primary purpose of staging? Is it pure fun? Increased delta V for a given payload? Increased reliability? Decreased reliability? Or decreased payload for a given delta V? Now, if we're talking about things like payload or delta V or reliability, we generally want to increase those. Those are generally considered good things. All else remaining equal, we want a system that's more reliable because it makes it cheaper in the long run. Now, if we have to spend more on the system to make it more reliable, there's a trade there. All else remaining equal, we would rather have more payload or more delta V or some combination thereof. So decreased reliability and decreased payload are not the kind of answers we're going to be looking for here. Now, if something was bad, so decreased costs for a given payload, yeah, we don't want things to cost more, all else equal. And I'm glad to see most of you didn't put pure fun. So if we look at the correct answer is delta V for a given payload, and that comes simply from the rocket equation. And it is pretty straightforward. Our rocket equation, our delta V, is a function of our ISP, or theoretical exhaust velocity, and that difference in mass, that ratio of masses. The bigger the ratio of masses, the more delta V you get. So if we're going to stage, our goal in staging is to try and reduce that M1. And ideally what we would do is we just burn our rocket. We haven't figured out how to do that. We can't burn our tanks up. We can't burn our engines. So instead, we can throw them away. Now that comes with a cost because there's extra structure, there's extra complexity. Now we've got to ignite engines at altitude, all of that stuff. That decreases reliability. There's a little bit of extra weight. And so we don't get infinite staging. And for our systems today, it's somewhere in the 2 to 3 stage range gives us the best performance. If we're looking at going further and further, you might get 3 to 4. But beyond that, the cost and complexity and reduced reliability and the like come into play. Now, as we said before, we are neglecting drag and gravity losses. So this works really, really well when you're up out of the gravity well in high Earth orbit and the like. As we get down from the ground, we lose some of that. But it gives us that kind of theoretical upper limit for that. Okay? Also in staging, just to remember, it is that sum. So if I ask you what the delta V of a 3-stage rocket is on, say, the exam, you start with the mass and you build your way down. That payload plus the stage mass, the burnout mass of that top stage, that becomes your top one. Then that plus the starting mass of your top stage is the payload for the stage below, and that one for the payload for the stage below. So it's just building it up. Actually, building it down is the best way to do it. And each of those delta Vs. The other nice thing about staging is ISP, or our VE. Because a rocket engine that works best on the ground isn't particularly efficient at altitude, and vice versa. And in most cases, we don't tend to use a single rocket engine from Earth to orbit. Anybody think of where we have burned one engine all the way up to orbit insertion? No? Yep. Okay, we've done it before. We don't need a single stage to orbit. Where very common launch system was used from, say, 1981 until just after 2010. Yeah, Space Shuttle. The Space Shuttle main engines were used all the way from launch on at sea level into orbit and did all the orbital insertion. They were designed as vacuum engines. And we'll do it again all the way up into vacuum with Artemis here. They have vacuum nozzles. They are not efficient on the ground. And if you ever watch a space shuttle launch, the video of a space shuttle launch, you'll see sock diamonds in the exhaust from the main engines on the ground. That's because they're overexpanded, the atmosphere's compressing, pushing it in. The solid rocket boosters, which provided the vast majority of thrust at launch. So the U.S. uses pounds force. Each Space Shuttle main engine at 110% throttle was about 450,000 pounds of thrust. We can convert that into meganewtons if you want. There were 3 of them. So roughly 1.3 million pounds of thrust. Each Space Shuttle solid rocket booster was over 3.5 million. So 7 million from just from those. So they were sea level nozzles. So if you watch near burnout, you'll see that the exhaust balloons outward. The plume balloons outward. That's because it's underexpanded. It's higher pressure than the surrounding atmosphere, so it pushes its way out. And that also is inefficient. There are engines where the same combustion chamber, the same plumbing, they change the nozzle on. So the Merlin engines on the Falcon 9s, they've got a vacuum nozzle on the upper stage. Different nozzle. In fact, when we get to the Atlas here in a minute, that one had the same engine, ignited all 3 engines at liftoff. 2 of them had sea level nozzles, 1 had a vacuum. Okay? What was the original reason for the 0 plus, so 0 plus 1, 0 plus 2 staging concept? Was it to create additional payload for a little additional complexity? Is it uncertainty over in-flight engine ignition, increased engine reliability, or increased commonality of parts? Now, before I get to the answer, one of these is correct for the original. It is no longer the reason we do it, and 2 of them are now the common reason we do it. And one of these is just wrong, not actually part of the consideration. So the reason we originally did it was uncertainty over engine ignition in flight. We had never tried to ignite a rocket engine at high altitude. We never tried to ignite a jet engine at high altitude. In fact, the times they burned out, we couldn't get them to ignite. So Korolev and the Americans at the same time decided we're going to ignite everything on the ground, and we'll just throw away the bits we don't need. So if you look at the original R7, it lit everything on the ground. And they actually have common engine nozzles for the strap-ons as for the core. Now the strap-ons have less fuel. They burn them at a higher thrust throughout the start of the mission, so they burn out first and then separate. And that's what we do now with things like Delta IV Heavy and Falcon 9 Heavy. But that is not because we can't ignite these engines at altitude, because us the ability to increase payload in those cases using the same parts. And all they do on Delta IV and Falcon 9 Heavy is you burn the booster engines at full throttle, and you throttle back the core after liftoff until the boosters run out. The other reason we tend to do it is, especially if we're using small additional solid rocket boosters like the GEMs on the Delta or the ones they use on the Atlas V, is it allows us to get additional payload for a little additional complexity. It's not the most efficient way of doing it, but unless you're launching this 30, 40, 50, 100 times a year, the cost difference in terms of op costs compared to development costs and that isn't worth that extra complexity. So for Delta IV and Falcon 9 Heavy, commonality of parts, and then the additional payload is the common one today. Okay? Why did the US use the 1.5 stage concept on the Atlas missile launch vehicle? 71% of you said the pressurized structure of the Atlas is very light. 43% said it's universally superior to 0 plus 1 and 14 2 stages. The answer, quite simply, is it is the structure of the Atlas V. So anytime we stage, we add complexity, we add weight. In the Atlas V, it's a pressure-stabilized structure. No one here has a... See, someone did in the last one. That's a pressure-stabilized structure. And to add that capability of having an upper stage would have required a lot of extra mass and the like. And the big heavy part that we didn't need anymore as we went up was actually just the engines. So we did that. We threw the engines away. So we ignited all 3 engines on the ground. we threw those engines away because that's quite light. If there was any damage to the walls of the pressure center, they tended to disintegrate, and that was really common. If you go to Marshall Space Flight Center or the Kennedy Space Center, they have atlases, leftover atlases, in their displays outside. If you walk next to them, you'll hear a hiss because they have to keep them pressurized. Otherwise, they will collapse on themselves. They cannot support their own weight if they're not pressurized because they're not stable. They buckle. When they launched John Glenn into orbit on the Mercury Atlas at the beginning, over 50% of the test launches of the ICBMs, the structure of the missile would fail on launch, and it would disintegrate, flamingly so. So it wasn't reliable enough to, say, kill a few million people, but it was reliable enough to launch someone into space. One of those weird things. Okay. Let's go to Q&A. Can we have a pizza party, please? Interesting. I control no pizza party budgets. Talk to Student Experience. See if they'll do something. I'm nothing against a pizza party, but don't have the budget for a pizza party. Okay. So we'll close that poll out, and we'll start the orbit transfer poll or survey. So the next bit, we've talked about launch vehicles, the concepts of staging and the like. Next bit, we're going to talk about orbital transfers, the different types briefly, and some of the assumptions. Okay, you can keep working on the poll as we start this. So the first one is, what is the lowest energy single burn transfer? Is it the HOMON, the tangent, the bioelliptic, or the fast? Now, before we get into the answer, just briefly, let's talk about what we mean by single burn, because this is a bit confusing sometimes. So I'm in this orbit here, and I want to go into this transfer orbit. A single burn in design is that injection burn that puts me on the transfer. We may have to circularize at the end, but we don't count that. Depending on where we're going and the uncertainties of how long our burn lasts or the exact thrust, we may have to do a mid-course correction or more burns along the way to make sure we get to our target. And that's especially important, say, going far away to Mars, because it doesn't take much error in duration of burn or thrust, and we don't know how much thrust a rocket produced. It's a model, to miss Mars. You don't need many arc seconds of error to, say, miss a planet, because they're tiny. I mean, even in navigation on Earth, it doesn't take a whole lot to miss something big. So back in the day, 40 years ago, 50 years ago, we used a navigation system for long distances called Omega. And Omega wasn't particularly accurate. Its whole purpose was to set off from some place like Newfoundland or San Francisco and be able to hit Ireland, which is small. Or if you went from San Francisco, to be able to find the Coast Guard cutter halfway to Hawaii, and then from there to be able to hit Hawaii. That's how inaccurate Omega was. So we're talking lots and lots of things. But a single burn doesn't count all of that. It's the transfer, it's the burn it takes to get into the place so that you're going to ultimately get towards the right orbit for your destination without all of that. We can add extra burns in there. Now, why do I say that? Because there are situations where more complex burns, more burn transfers may be actually lower energy. But if we're doing a single burn, the lowest energy is the HOMON transfer. And as I said, there are cases where the bioelliptic, plenty of cases where the bioelliptic is actually a lower energy. So there are situations where we're trying to get from Earth to geosynchronous, geostationary orbit, where it's actually good to go into a higher orbit transfer ellipse and then up there burn to bring it back down. Big negative. What are the major disadvantages? 59% of you said time, 41% of you said it's incompatible with low thrust systems, 38% of you said incompatible with high thrust systems, and 29% of you said fuel burn. So if it's the lowest energy transfer in most cases, it's not going to be fuel burn. Okay? Obviously, if we add that complexity of, say, a gravity assist flyby of Venus or any of that, obviously it will have higher fuel burn. The biggest ones are time and incompatibility with low thrust systems. HOMONs, quite strictly, is an impulse burn transfer. Now, we don't produce impulse burns. What's the acceleration on an impulse burn? Anybody know? True impulse? Yeah. So what's the acceleration? Infinite, right? So we never do that. We have higher and lower thrust systems and burns, and our real burns look much more like this. Get that across. So we have finite duration burns here and here for HOMON transfer. Now these burns, the reason we impulse is the duration of those burns is substantially less than the transfer duration. So as I said, when we do the Artemis mission to go to the moon, if it launches in February, the translunar injection burn. So the one there close to Earth that takes us out of Earth orbit, sends us on the path to the moon, that's going to last for 30 minutes, half an hour. But we're talking a day and a half, 2-day transfer, 36, 48 hours of transfer. So, you know, you're talking a few percent of the time of that transfer. So that's close enough. High energy burns, we burn, we keep burning. High thrust, we do these weird injections. That's there to get us quickly. That's why we do those type of missions. If we have a very low thrust chemical, we might just constantly put ourselves on higher and higher orbits and then intersect this orbit that we want, whatever it is, with the least tangential velocity. So it's a tiny, tiny burn. So many here, one there. And of course, electric propulsion, which is typically low thrust, we would just burn continuously out, 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 and then turn it around and burn into that orbit. If we had high thrust electrical, we could go far, far, high thrust, high efficiency, and you flip halfway through and burn on the intern, take it in. Okay? And as we said, an impulse burn is instantaneous acceleration and infinite acceleration. Okay. Question answers. What's RP in the delta V equation? So the rocket equation. Are we talking about this one here? Yeah. Ah, yes. Yeah, so RP, this is changing orbits. RP, oh, this is on the HOMON, sorry. Yeah, this is the radius of the periapsis. And A being the semi-major axis of your transfer orbit. Yep. Mm-hmm. So VP, periapsis, VR1. So yeah, periapsis of your new orbit, your transfer orbit, versus VR1 is the velocity of your, in this case, circular orbit. Okay, this is, mu is the gravitation vector, it's a gravity well. It's the gravity, so it's where, so mu here, it's the mass of your major body, the Newton's gravitational constant, and the radius. It's the same thing we have in escape velocity. Okay. Well, quickly enough through those. We will do the miscellaneous survey. We'll talk about that We have a little bit more time this time to do it. Okay, let's go to the first question on our miscellaneous survey. True or false? Getting up, launch, is harder than getting down, entry. Now, both of these are hard. In space, the natural state of anything is failure, and when things go wrong, they go really wrong. So on launch, either the vehicle itself disintegrates, blows up, or, it seems it's going off course. What do we do? Blow it up. But getting down is always the more complex operation. You've got to get your entry interface right. The wrong angle, the wrong orientation of the spacecraft, much, much worse. So in reality, while both are hard, we tend to have more failures on entry and capture. You can hit the atmosphere on an arrival, direct arrival from a transfer orbit from another planet, and you'll bounce off. You literally can bounce off the atmosphere. Or it's too steep, too high a velocity, you burn up. And then finally, even when you have lots of good atmosphere to slow you down, the drag alone on its own isn't going to fix it. So if you don't burn up, you don't miss. If your parachutes or your retro rockets don't work, bad things happen. That was a comet return mission. Needless to say, the parachute failed. Did contaminate the stuff. They did get some science out of it, but it was quite disappointing. Soyuz. To fly on Soyuz, there's a minimum and maximum height you can be from the bottom of your feet to the top of your head, because they have specific couches they build specifically for each cosmonaut and astronaut. And the reason why is if the retro rockets fail to fire when they land on the ground, they didn't have those, you'd be at risk of severe spinal injury. In Apollo, that was the corner design case. If they had to do an abort on launch and the winds were such, instead of splashing down in the ocean, it would have landed on the ground in Florida. It didn't have retro rockets. How do you ensure that the crew aren't killed by landing on the ground instead of in the ocean? So while getting up is very hard, getting down is just a little bit harder. Okay? True or false? Ducks have the ideal shape for a reentry vehicle. So these are from our high supersonic speed tunnel. It's our high supersonic and hypersonic tunnel. This is the standard spoiler plate of a space capsule design. You've got a very high radius bottom conical shape. When you're launching, the flow comes in this way, entry that way. We see a nice, clean, detached shock wave, and that's a good thing. Because that shock wave, there's extremely high temperature, high energy flow here. But you'll see none of it really impacts the capsule. It's deflected around. When you're entering the atmosphere, that will be ionized flow. So instead of just oxygen and nitrogen, we now have O+, N+, negative electrons flying around. Really, really bad for radio waves. That's why we get blackout on entry. It's from that ionized flow. If we say choose a Millennium Falcon or a cat or now our duck, not so nice. We have relatively sharp points where instead of being well detached away from the body, that shock wave is now up against the body. That's a point of extra heating. We have to deal with that. We also get interactions of shocks and then shocks in the body. Really, really high heating points. If this is bad, this may be 5, 10 times worse. We'll burn through. When we have burn through, that's not so good. A la Space Shuttle Columbia. Because internal structure of spacecraft are not designed to take those heating loads or those loads. Okay? Those of you who are Millennium Falcon fans, it's a pretty crap design for atmospheric flight. Obviously, in sci-fi, you might have deflector shields or the like that may change that flow, but you wouldn't naturally want to fly that through the atmosphere at any speed. Does the video still work? Lots of interaction. See, this shock wave is impacting there. That would break off or burn off pretty quickly in real flight. Okay. Finally, the last of the questions on this survey. Which takes more delta V for the lowest energy transfer from Earth orbit to orbit around the body, the Moon or Mars? And it's the Moon, which isn't intuitive to most people. And why isn't it intuitive? Well, the Moon takes more, but our rockets and stuff to go to the Moon with people on board are a lot smaller than what we propose to take people to Mars. Why is that? Anybody tell me why, even though the delta V's from orbit to orbit, LEO to below Mars orbit and LEO to lunar orbit, are the delta V for the Moon's higher than it is for Mars. Why is the spacecraft to go to Mars design, why is it so much more massive than the spacecraft to go to the Moon? Yep. Okay, getting into and off Mars requires more energy. But let's say, well, Mars we have the ability to do aerobraking. But all of our fuel for the return, both on the Moon and Mars. It would still be much larger to go to the Mars than the Moon. Why? Yeah. Yeah. Humans require lots of supplies. The transfer from LEO to lunar orbit is a couple of days. Also, you can basically fly back from the Moon anytime because it's in orbit around the Earth. So you don't have to stay there very long. So a lunar mission might be a week. You know, you can make it longer, but you don't have to. Mars, our transfer is maybe 160 days each way. Spend 6 months or a year on the surface. A lot of supplies. Even if we were really good at recycled all of our waste products back into water and the like, grew our own food, and like all of the just natural losses in entropy, you're still talking about 20 kilograms per kilogram of human of supplies to go to Mars. So our spacecraft get much, much larger. As we said, it takes a lot more energy to get into. We have to take a lot more energy out on descent into Mars from Mars orbit and launch again from Mars than from the Moon. But just those interplanetary transfers, much, much lower, or lower, not much lower, but lower delta V for those. Okay, we're a little ahead of where we were last hour, so we get a chance. We'll do some questions. Are those images of wind tunnel tests made using Schlieren? Yeah, I believe those are Schlieren. Some of the ones that did, and it was a former PhD student of ours who now works for BAE Systems running their wind tunnels up at Wharton, up outside of Preston. I think he used another technique for some of them called background-oriented Schlieren, but those are proper. Some of those are Schlieren. Okay. Before we go anywhere else, just take a few minutes. There is no right answer. It's just kind of fun. The favorites survey. So there's 2 favorites questions, and we'll just let you guys fill this out. Last hour, we had some real and some fictional answers. That's fine, and we'll go through them. So the question is, are we going to learn how to design wind tunnels? I don't know. I won't be telling you how to design wind tunnels. In fluids, you'll talk through the stuff that you would need to consider for wind tunnel design, and you do some wind tunnel experiments. Yeah, so we do have a unit in our 4th year on hypersonics. And we do use that wind tunnel, so you will go through the process of how to set up the optics and all of that. Or, yeah, I think you do use that tunnel. So only 2 of you. 3 of you have. Okay. You're welcome to keep putting stuff on there. Let's just see what people's favorite spacecraft is. Voyager 2. Voyager 1 gets some love today. The Death Star, interesting. ISS, Sputnik, Soyuz, in one version or another. Ingenuity. Would you define Ingenuity as a spacecraft? Interesting question. Not going to tell you. Crew Dragon, Apollo, Spacecraft, Wallace and Gromit, Cheesecraft. That's a new one. The Imperial Star Destroyer. No love for the Super Star Destroyer. X-Wing, Dragon 2, X-Wing Galileo, Challenger. Vostok 1, yep, that's a good one. Okay. So I'm not sure how it decides which one to put up as big. Speaking of Voyager 1 and Voyager 2, anybody know which one was launched first? Yeah.
Let me guess, Voyager 2 was launched first?
Yeah. So they launched Voyager 2 before Voyager 1. I don't remember, it was 4 or 5 months. And the reason they changed the names is Voyager 1 was on was a quicker arrival to Jupiter and Saturn. And then departed, went basically normal to the ecliptic, part of the solar system. Voyager 1 took a much longer journey, then went past other outer planets and the like. So they swapped one departed that way, 2 and that. So they swapped it over. So interesting thing about the USS Enterprise. There are real USS Enterprises. Anybody know what the most recent USS Enterprise was? Yeah, it was an aircraft carrier. It has a long history. There have been Enterprises since early in the U.S. Navy, hence why Star Trek used the Enterprise. There was a space shuttle, non-orbital vehicle, so an atmospheric flight test vehicle, known as the Enterprise, and it was actually named after the fictional USS Enterprise of Star Trek. My BMX, that's an interesting one. If you get it into orbit, that'll be, that Tesla Roadster of Elon Musk is now a spacecraft. Okay, your favorite launch vehicle, Falcon Heavy. All are amazing. The emoji ones. That's strange. Iron Man. The Soviet N-1, which wasn't very successful. Was it 2 or 3 unsuccessful launches? So the interesting thing about the Soviet N-1 was the Soviets had a real challenge at the time developing large rocket engines. So where the U.S. built large single nozzle, single chamber F-1s, the Soviets were still basically on small chamber engines with multiple nozzles. To get the required thrust first stage of the N-1, they used something like 36 engines. And the engines and all the support structure, they suffer what's called the Pogo Effect. So those engines in the center, long arms to what they're attached to, would bounce up and down. And the vibrations cause the rocket to break apart. Saturn V, believe it or not, also suffered from the Pogo Effect. The 5th engine, the center engine, would bounce up and down. And one of the missions, they actually had to shut the engine down early because they were afraid it was going to cause it to break up. And the like. There's an interesting story on Space Shuttle where they almost shut down 2 engines due to some sensors that were wrong. And the flight controller that was observing it hit the cancel button because he realized that if the engines were failing, they were going to blow up and everybody would die. But if they shut down the 2 engines, they were guaranteed that everybody would die. So he took the chance that they might die over they will die. But the actual routine, the software said, better to take the known than the unknown. Okay, Saturn V, Iron Man, everything. Any other ones? Starhopper, Madagascar 2. A trampoline, that would be an interesting one. That would take a lot of energy input into your trampoline to get up there. I'm surprised no one said guns, the Bull's cannon that was never built. Okay, so that's the end of those questions. Let's see if there is any more Q&A. Nope. So that's it. So next week, we're going to talk about propulsion. So all that stuff on ISP, we'll talk about that. We'll talk about TSFC and the like. And in 2 weeks, we're going to be talking about artifacts of import. One of the items in there is no longer strictly true, or part of it's no longer true. It went false sometime in the past year. So challenge for you, one of the first questions will be, what was it that isn't right anymore from it? And we'll talk about that story in a little bit. Don't answer it now. Any other questions before we run away for the day? Yeah.
So we're finally
Yeah, we'll talk about that.
just in case you examine.
No, I won't examine you on it. It's amazing how that history lived. So that's in 2 weeks. Anything else, guys? If not, have a good one. Enjoy the rest of your day.